Hi everyone. So in the last couple of videos, we talked about how you can find the slope of the tangent line to a graph at a particular value using something called the limit definition of the derivative. And so in this video, we're going to continue that discussion, but we're basically going to see what the connection is between all of the different slopes of tangent lines on your graph. And we'll see that if you take all of those different slopes you get at different points and kind of put them together in a certain way, they actually give you another function called the derivative function. So just to remind you, we talked about this in the last video, or maybe it was 2 videos ago. If you write down this f prime of a, and typically you'll be putting a number in, like f prime of 1 or f prime of 2 or something like that. You can read that out loud as I just did as f prime of a, but what it really means is it's the slope of the tangent line at the x value of a. And then the other name for it is that's the derivative of f at a. So f prime of a, the derivative of f at a, and the slope of the tangent line at a, those all mean the exact same thing. They're just different names for the exact same idea. So how do we actually go about finding this? Well, as we saw in the last couple of videos, we do this limit. And so what does this limit look like? Well, in the numerator, we're plugging whatever our number is. So let's say it's 1, you would be doing f of 1 plus h and f of 1, and you subtract those. And then in the denominator, you have h. And then you're taking the limit as h approaches 0. And just to remind you where this comes from, because I would really like if you rather than just kind of blindly memorizing this, if you kind of understand why this works. So this part here is the slope of the secant line between 2 close by points, right? So whatever a is, that's your place where you're trying to find the slope. And then this plus h means that you're just looking at a point that's very close by. And if you find the slope of the line that goes between those 2 points, you'll end up subtracting f of a plus h and f of a, and then in the denominator, you'll have a plus h minus a, which just gives you h. So this part that I circled is just the slope of a secant line between 2 close by points. And then why are we doing a limit? Well, we're taking the second point closer to the first point. And the way that we can accomplish that, so because the second point is supposed to be a plus h, if we bring h closer and closer to 0, that will have the effect of bringing the second point closer to the first point. So that's where this definition comes from, just to remind you. So what I want to do to start off in this video is I want to kind of make a table and find some different slopes of tangent lines for this function so that we can kind of start to see what the relationship is between those different slopes. So we're going to fill out this table, and there's one value that we already found the other day, right? We know that the slope of the tangent line at x is equal to 1. We know that that's equal to 2. Right, that's one that we did actually way back at the beginning of the quarter, and then we also did it, I think, like 2 videos ago. Move this down a tiny bit. So what I want to now do in this video is find the slope at -1 and the slope at 0. And I would really recommend that you pause the video and you try to do those yourself just to make sure you remember how this whole process works, and then come back and we'll go over it together. So we're going to just use this definition that I wrote out here to actually calculate the slope at -1, and then we'll do it at 0 as well. So how does this work? Well, we basically just want to plug -1 in for a. So we're finding the limit as h approaches 0 of f of -1 plus h minus f of -1 all divided by h. And then what is -1 plus h? Well, that's going to be negative, or what is f of -1 plus h? That's -1 plus h squared, right? Because our function is x squared. So we have -1 plus h squared minus, and then f of -1, well, that's -1 squared. So I'll just put that in here over h. And then if we multiply all that out, we're going to get, so -1 times -1 is 1, and then we have minus 2h plus h squared, and then -1 squared is positive 1, but then we're subtracting it, all divided by h. And so notice that this 1 and this 1 are going to cancel out. So we're left with the limit as h approaches 0 of negative 2h plus h squared over h. And now we can factor out an h, right? So we have the limit as h approaches 0 of h times negative 2 plus h divided by h. And we can cancel out these h's. And then we get the limit as h approaches 0 of negative 2 plus h. And so we could never plug in h equals 0 up until this point because we always had an h in the denominator, but now we don't. So now we can plug in h is equal to 0, and so we just get negative 2. So we now know that the slope of the tangent line at x equals negative 1 is negative 2. And I'll come back to talking about how maybe we could have actually figured that out without doing this limit, but I just wanted to, I want to do the next one first and then we'll come back to that. So let's also do 0. So the slope of the tangent line at 0. So we're going to get the limit as h approaches 0 of, this time we have f of 0 plus h minus f of 0 all divided by h. So that's going to be the limit as h approaches 0 of, so f of 0 plus h, that's just the same thing as f of h, right? The 0 plus h is just h. And so f of just h is just h squared. And then 0 squared is 0. So the numerator is just h squared minus 0 over h. So this simplifies to the limit as h approaches 0 of h squared over h. So now we can cancel out one factor of h, and we're left with the limit as h approaches 0 of just h. And now we can actually plug in 0, right? Because we're not dividing by 0 anymore. Now we just have 0 as our answer because we can just plug in 0 for h. Okay, so let's put that on our table. So before we get to the next thing, I just want to point something out, which is that, so we already knew that the slope of the tangent line at 1 was equal to 2 from before. And so it makes sense that when we did the same thing at negative 1, that we got negative 2 as our slope, right? Because there's some symmetry in this graph. So the slopes on the left and the right, if they're across from each other, they're going to be the same value, but just positive or negative. So it shouldn't be too surprising that we got negative 2. And then also shouldn't be surprising that we got a slope of 0 at 0 because there's a horizontal tangent line, right? Anytime you have a parabola or any kind of similarly shaped graph, it's always going to have a horizontal tangent line at that place where it's kind of changing direction. Okay, so what I want to do next is we're basically going to think of this, this table that we made. We're going to think of this as though it's just a function. So forget about tangent lines, forget about all of that. Pretend that you're back in like some basic algebra class and someone gave you this table and they just said, here are our inputs and here are our outputs, graph this. So what would you do? Well, you would just go to each of these values and graph them. So we'd say, okay, we have negative 1 is our input, negative 2 is our output, so we have a point here. When 0 is our input, we have 0 as an output, and so that's this point here. And when 1 is an input, 2 is an output, so we have this point here. And if you start to notice like what is going on here, well, this forms a shape of a line, right? So if we were to continue this, we have a line, and specifically a line with a slope of 2. So this function that I just graphed here, this is what's called the derivative function of f of x. So I'm just going to change one subtle thing here, and it really isn't a big deal. I'm just going to, instead of writing this as a and a, I'm just going to change it to x. And that doesn't matter, right? You can use whatever letter you want when you're talking about a function. We could use w, we could use t, we could use z, you can use whatever letter you want. I'm just going to use x because that's the more kind of conventional way of doing it. And so this picture that we have over here, this is a function that is called f prime of x. And so the way that this function works is that at every point on this function, the x value refers to an x value on your original function, and then the y value refers to the slope of the tangent line at your original function, right? So the reason that this point here is on this graph is because at an x value of 1, the original function had a slope of 2. That's why that point lies on this graph. And then similarly, the point, and we didn't do this one, but the point 2,4 lies on the graph. And so why does the point 2,4 lie on the graph? Well, because if you go to an x value of 2 on your original function, the slope, and it happens to be also on this graph that when x is 2, y is 4, that's a coincidence. I don't want you to think too much into that. What this is telling us is that the slope of the tangent line at 2 is equal to 4. So the way that this derivative function works is that it basically just kind of carries all this information. It tells you at every single x value what the slope is on the original function at that x value. I know that's kind of a difficult concept, so that's basically like what we're going to be talking about in this video. We're going to do a lot of practice with like making sure you really understand what that means and how that works. So what is the equation for this derivative function that we just drew? Well, just like any other function, if someone gave you this graph and just said, hey, what's the equation for this graph? You would say, okay, well, it's a line with a slope of 2 going through 0. So the equation for it is 2x, right? Just forget about the fact that it represents anything related to slope. Just think of it as a normal function. So this normal function is a line with a slope of 2, and so its equation is f prime of x is equal to 2x. So, we figured out that the equation of this was 2x by basically, plotting points and just kind of making sense of it. But there's a better way to do it, which is basically that instead of doing this limit definition with each individual x value, we can just do it with x instead of each individual x value. And then what that will give us is it will give us a function, right? Like when we did these limits, our answer was a number, right? Why was our answer a number? Well, because we were plugging a number in here, right? And so the only thing we were left with at the end was h, and then we would plug that in as 0, and then we were left with a number. And so what we're going to do next is instead of having a number here, we're just going to put a variable x. And that will give us a general formula that tells us the slope of the tangent line at any x value. So rather than having to do this over and over and over to find the slopes at every different point, we're now going to have a general formula that we can plug any x value into. So let's see how that looks. So let me just kind of summarize what I just said here. So instead of calculating f prime of a individually for each x value, right? We did it for -1, we did it for 0, we did it for 1 the other day. We can do it all in one go. And the way that we're going to do that is literally we're just going to replace a with x, and we're just going to say f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And we'll go through and do this for this function right now. And basically what we'll see is that we will get 2x as our answer, because we already know, right, that that is the correct answer because we just saw it up here. But let's actually see how that plays out. So we need to figure out what f of x plus h is, right, first. That is going to be part of what goes into our formula. So f of x plus h, if we have f of x is equal to x squared, f of x plus h is going to be x plus h times x plus h. And that's going to give us x squared plus 2 times x times h plus h squared. And so now we can put that into our equation. So f prime of x is going to be equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus, and so now we have to subtract f of x, and f of x was just x squared, right? That's just our original function, all divided by h. And then we'll see that this will basically play out exactly like the examples we did above, except for that we'll have an x left in our answer. So let's simplify the top first. So we can see that these x squareds are going to cancel out with each other. And so we're going to be left with the limit as h approaches 0 of 2xh plus h squared over h. And then just like we did on the earlier example, we're going to now factor out an h from everything. So we have the limit as h approaches 0 of h times 2x plus h, all divided by h. And now we can factor out this, or sorry, cancel this h. And we're left with the limit as h approaches 0 of 2x plus h. And now we can plug in 0 for h, and we're left with 2x. So what does this mean? Like, what is this telling us? This is telling us that for any x value, if we want to figure out what is the slope of the tangent line to f of x is equal to x squared at that x value, we just have to plug it into the function 2 times x. And that will, for any x value, tell us the slope at that point. So let me write that down. So our equation we just came up with was f prime of x is equal to 2x. And this gives us the slope of the line tangent to f of x is equal to x squared at any x value. So all we have to do is plug the x value we're trying to find the slope for into this function. So for example, let's say we wanted to find f prime of 1. So we already know that that's equal to 2, right? But we can see that again by just plugging it into this function. So 2 times 1 is equal to 2. But what's really nice is now we can do other values other than the ones that we already calculated. So for example, if I want to know, well, what's the slope of the tangent line at negative 0.6? Well, without having to calculate an entire limit again, I can just say, oh, well, it's just going to be 2 times negative 0.6. And so it's going to be negative 1.2. Or if I wanted to know what's the slope of the tangent line at x is equal to 100, I just plug in 100 and I say, oh, it's 2 times 100, so the slope is apparently 200. So we can now find the slope of the tangent line at any x value using this formula. And so that's really the power of coming up with a derivative function rather than calculating the derivative for each individual x value. So we're going to do this for a couple more functions, this process of doing the limit. But the other thing I want to emphasize in this video is, again, this kind of connection between what the graph of the derivative function looks like compared to what the graph of the original function looks like. And I think this is probably one of the trickiest topics in like all of calculus, is really being able to understand this connection. So it's okay if you don't totally get it. We're going to definitely go into more detail with this in the next video, and then like basically all throughout the quarter, we're going to keep coming back to this idea. But again, just to remind you one more time, so this graph in blue, the way that it works is that every x coordinate corresponds to an x coordinate on the original function. They're the same x values. But the heights, the y values on the derivative function, those tell you the slopes of the tangent lines on your derivative. So one way that that kind of shows up is that if you think about whether your function is increasing or decreasing, that will correspond to whether the derivative function is positive or negative. So what do I mean by that? Well, remember, decreasing just means that as you go from left to right, the function is going down. So this function is decreasing at this part of it, right? This is decreasing. It's going down from left to right. And if you look at the derivative function, what's going on with the derivative function? Well, all of this part of the graph, it lies below the x-axis. So this part of the graph is negative. So I want to be really careful. When I say the word negative in this class, all I mean is below the x-axis. And when I say positive, I mean above the x-axis. So I really don't want you to confuse the words negative and decreasing. Decreasing means it's going down. Negative just means it literally lies below the x-axis, regardless of whether it's increasing or decreasing. So this next part of the graph here, this is increasing, right? It's going up from left to right. And so if a function is increasing, that means that it has positive slopes, right? If you were to draw all the different tangent lines on the part that's increasing, they would all give you positive slopes. And so that's why when you look at the derivative function, the y values are all positive on this part of the graph, because all of the individual slopes, if you calculated the slopes at every different x value in the green part of the original function, every time you calculated a slope, you would get a positive number. And so you'd go and plot those points on your derivative, and they would be above the x-axis, because you would be plotting points like 1, 2, or 2, 4, points where your y value is reflecting that positive slope on the original function. So what's the one point we didn't mention here? Well, at 0, we talked about how the function has a horizontal tangent line. And so that means it's neither increasing or decreasing, right? It's just kind of flat. And so when the derivative function, when the original function is neither increasing or decreasing, that corresponds to the derivative function being 0, or having an x-intercept, right? Because like at x is equal to 0, there's a horizontal tangent line, and so that means we have to plot this point as 0, 0. Okay, so we're gonna, like I said, let me just see if there's anything else I want to say about this example before we move on. I don't think so. So let's move on to another example. And actually, let me just write out one kind of general fact before we get to the next example. So in general, if f of x is a function, then f prime of x is called its derivative function. And so the way that f prime of x works is that it tells you the slope. So f prime of x tells you the slope of the line tangent to your original function at any x value. And when I say it tells you the slope, what I really mean by that is that just like any function, the derivative function is a function. And so it has an input and an output, right? And so the input for the derivative function is an x value. And the output, I didn't really leave enough space here, I'll put it down here. The output of the function is the slope of the tangent line to your original function, to f of x, at that x value. And so that's exactly what we saw on that previous example, right? And so how do you find f prime of x? You have to calculate the limit. And so we're now going to be doing the limit as h approaches 0 of f of x plus h minus f of x over h. So this is now our kind of new limit definition, because now we're not doing it individually for each number, we're just doing it with x. Okay, so I want to do a couple more examples. And so for both of these, we're going to start by just using the limit definition. And then we're going to look at the graph of the derivative function and kind of try to make the same comparisons that we did on the last example in terms of increasing, decreasing, positive, negative, that kind of thing. So this function is f of x is equal to 1 over x. So we can kind of ignore the graph for a moment because we're just going to focus first on finding the limit or finding the derivative. So f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And so just like with the last one, we want to plug in what this actually looks like. So f of x plus h is going to be 1 over x plus h, since our function again is 1 over x. And then we have minus 1 over x, all divided by h. And so what we'll see with these examples is that all of the same techniques that we've been using for limits, so making common denominators, multiplying by the conjugate, expanding things and canceling, we're going to be using those exact same methods. It might feel a little harder just because we have two variables now, right? We have an x and an h, but it's technically not actually harder. It's really the exact same algebra. It's just that you have to get used to seeing an x in there and try not to get intimidated by that. Okay, so how are we going to tackle this? Well, we want to make a common denominator, right? And so the way to make the common denominator is to multiply the first one by x over x and the second one by x plus h over x plus h. So it looks a little scary right now, but it will look simpler in a moment. So now we have the limit as h approaches 0 of x over x plus h, or sorry, x times x plus h minus x plus h over x times x plus h, all over h. So we talked about this in one of the previous videos. Make sure that when you're subtracting this fraction, it's as though you have parentheses around it. So you want to distribute the negative sign to both parts. That's probably like the most common mistake I see people make on this kind of problem. So we end up in the numerator with x minus h, all divided by x times x plus h, all divided by h. And so that simplifies to x minus x is 0, and so we're left with negative h over, let me move this up a little, negative h over x times x plus h, all over h. And we're almost done. So the next step is to rewrite this division as multiplying by 1 over h. So we're going to rewrite this as times 1 over h. And so now we can cancel out this h and this h. And so we're left with the limit as h approaches 0 of negative 1 over x times x plus h. And so now we can actually plug in 0 for h, right? And we end up with negative 1 over x times x, because that becomes x plus 0, and so we're left with negative 1 over x squared. And so what this tells us is that the derivative function of f of x is equal to 1 over x is f prime of x is equal to negative 1 over x squared. That's the derivative function of f of x is equal to 1 over x. And so what is the value of this? Well, we can use the derivative to find slopes of tangent lines, right? So for example, let's say I wanted to know, what is the slope of the tangent line at 2? Well, then I would just say, okay, f prime of 2 is equal to negative 1 over 2 squared is equal to negative 1/4. So now I know that the slope of the tangent line at 2 is negative 1/4. Or if I wanted to find what's the slope at, let's say, negative 3, I would say, okay, I need to plug in negative 3 into this derivative function, and the slope would be negative 1/9. So, and let's just kind of look visually at this and see that that makes sense. So I think we actually did an example with this function in a previous video, but visually it makes sense, right, that the slope of that tangent line could be negative 1/4, and then at negative 3, it looks also like, this could be negative 1/9 as a slope. Okay, so what does the derivative function look like? So it's negative 1 over x squared, and I actually have that graphed hiding over here. So let me just move it back. Sorry, it's getting a little stuck. There we go. So this is the graph of the derivative function, f prime of x is equal to negative 1 over x squared. Looks like this. And so, for example, I just want to point out that at x is equal to 2, this the y coordinate of this point would be negative 1/4. And why is that? That's because, well, we just calculated that below, and that corresponds to the fact that the slope on the original function was negative 1/4. And then at negative 3, the y value of that point is negative 1/9, because we found that the slope of the tangent line at negative 3 on the original function was negative 1/9. So you want to think of the derivative function as kind of like a carrier of information about the original function. It carries all this data of what all the different slopes of the tangent lines are. So I just want to point out a couple of things to you. And like I said, we'll be getting more into this in the next video. But if we look at this function, 1 over x, notice that it's actually always decreasing. Right? Like if you go from left to right, the function's always going down. So this part is going down, right? And then if you look at the other part of the graph, that's also going down. So there's no part of this graph that's going up from left to right. It's always decreasing. And so that's why this graph is always negative. And when I say negative, again, I mean below the x-axis, right? There's no part of this graph that lies above the x-axis. The other thing I just want to quickly point out, and we'll get more into this in the future, is that notice that the original function has a vertical asymptote. And so that means that there is no value at 0, right? The function is undefined at 0. And so notice the derivative is also undefined at 0. The derivative also has a vertical asymptote at 0. And then another thing I just want to point out is that notice that as you go this way, the slopes are getting less and less, right? The function starts off really steep, and then it's kind of flattening out. And so that's why if you look at the derivative function, the graph is getting closer and closer to the x-axis, because we're getting these slopes that are like negative 1/4, negative 1/9, negative 1/16, negative 1/25. So you're getting these really, really tiny fractions. And so that's why both graphs are kind of flattening out to the x-axis. All right, one more example. Same kind of procedure with this one. So this time we're going to look at f of x is equal to the square root of x. So again, I want to start by finding the derivative function. So we're going to use that same limit definition. So in this case, our function is square root of x. So that means that if we do f of x plus h, that's going to be the square root of x plus h. And then we have square root of x. So what method are we going to use in this case? Well, this is going to be a multiply by the conjugate example. So what is the conjugate in this case? Well, we just want to take this negative sign and flip it to positive. So we're going to end up with the square root of x plus h plus the square root of x. And then same thing in the denominator. Okay, so how does that work out? Well, when you multiply those two numerators together, the square roots are going to cancel out. So we'll have x plus h, and then we have minus x. And then in the denominator, we have h times the square root of x plus h plus the square root of x. And so this is going to give us, in the numerator, we're just left with h. And then in the denominator, we have all this stuff. Okay, so now we're again in a situation where we can cancel out our h's. And so now we're left with the limit as h approaches 0 of 1 over square root of x plus h plus square root of x. And so now we can actually go ahead and plug in 0 for h. So now we have 1 over the square root of x plus the square root of x. And another way of writing that would be 1 over 2 root x. So really when you're doing these, the algebra should feel very, very similar to what we did before. It just kind of looks more complicated. So that tells us that the derivative function is f prime of x is equal to 1 over 2 root x. So again, just to kind of give a quick example, let's say we wanted to find the slope of the tangent line at x is equal to 4. Well, we would then plug 4 into the derivative function and we would get 1 over 2 times the square root of 4, and that would give us 1 over 4. So the slope of the line tangent to the original function at x is equal to 4 is 1/4. Or if we wanted to figure out what's the slope of the tangent line at x is equal to 16, well, we would plug 16 in. And we would find out that the slope of the line tangent to the graph at x is equal to 16 is 1/8. Okay, so once again, I want to make that connection with the graph. So let me go grab the graph that's hiding over here. So this is the graph. If you were just to go into, Desmos and type in y is equal to 1 over 2 root x, this is that graph. So this is just the graph of the derivative function. So again, just to point something out, like we found that the slope at 4 was 1/4, and so that means that this point here has coordinates for 1/4. It has a height of 1/4 because that's the slope on the original function. Okay, so I just wanted to do that same kind of thing that we did with the last one and think about, where is the function increasing or decreasing? So notice that this function is always increasing, right? It's going up from left to right. And if you think about what the graph of the square root of x looks like, it never goes down. It's always increasing from left to right. And so that's why the derivative function is always positive. So this has a horizontal asymptote. It never goes below 0. So this graph is always positive because all of the slopes of the tangent lines on the original one are positive. So there's no way the derivative could be negative. There's also something kind of funny going on at 0, and we'll talk more about this, I believe, in the next video. Basically, because the function just kind of cuts off here, the derivative is undefined at 0, and so what ends up happening is that on the derivative function, you have a vertical asymptote. And a couple other things I want to point out. So one, it's kind of hard to see here, but if you look close to 0, if you were to zoom in on this graph, it gets steeper and steeper and steeper as it gets closer to 0. And so that's why the derivative graph is going up and up and up, because the slopes, if you were to really zoom in close to 0, the slopes would be really big. And then if you look at the general trend as the graph goes outward, it's kind of flattening out, right? The slopes it looks like it's getting less and less sloped upward. And so that's why the derivative function is sinking down towards 0, because those derivative values are just, not that big. The graph is coming closer and closer to a flat slope. All right, so that is it for this video. Like I said, these ideas we're going to continue working with in the next video, as well as really throughout the course. So this is really just kind of the first preview of this stuff. All right, I'll see you all in the next video.